Hi, thanks for watching this video about our paper Modern Learning with Pi, Personalized Interpretability Estimation. I am Marco Virgolin, and I did this work together with Andrea De Lorenzo, Francesca Randone, Eric Medvet, and Mattias Wahde. We know today that explainable artificial intelligence is increasingly important. For example, in healthcare, doctors need to want to use AI, but must understand why an AI makes a recommendation before making use of that recommendation. In biology, we can use AI to discover complex interactions, but we could extract even more knowledge if the nature of the AI will be transparent. And last but not least, lawmakers are increasingly asking us to produce AI that is safe and accountable. There are two main types of XI I want to talk about here. The first one is perhaps the most famous, thanks to the success of deep learning, and it's about explaining black box models, so something like our typical deep neural network. Some of these algorithms are basically features importance estimation algorithms, and what they do is they take in input your black box and a data point, and their output is an explanation of why the black box made a certain prediction. They come with their own limitations, which is explanations don't necessarily have 100% fidelity. So whether you trust the black box goes through the fact that you trust that the explanation is correct to begin with. Explanations can be local, which means that an explanation for given to similar points, the explanation may look actually quite different. So there's up to so much that you can learn from them. And last but not least, explanation can be at times false friends. That is, the prediction may be incorrect, but the explanation may look reasonable, inducing you into believing that the prediction is correct. The second type of XI I want to talk about here is about those algorithms that are meant to learn models that are transparent and interpretable. So these algorithms take the data set in input and produce an output, and there's something like decision tree construction, linear regression, rule set search, and so on. Another example is symbolic regression, where we typically manipulate some data structures to represent some symbolic formulas. A nice property of something like this is that you can understand how this formula is going to behave no matter what input it receives inside. Another nice thing is that you may be able to immediately see if some unwanted bias has been picked up from the data. In this case, there's a decision tree, which is putting males in an advantaged position. Okay, but also, of course, these methods have their own limitations. For example, the fact that these models now are less complex may mean that we need to put complexity into feature engineering by hand beforehand. If the relevant features you need for a good prediction are just too many, you may just need a model that is too large to be able to have a model that is interpretable anyway. Imagine a linear regression with 10,000 terms that all matter. And last point is that in principle, this algorithm can produce something that is hopefully interpretable, but the question is, can we optimize so that interpretability will be achieved? So that's not a guarantee, right? All right, and often these implementations to answer this question boil down to something like this. We want to find a certain model that minimizes a certain loss, where we have our features and our label. And this loss is penalized by some sparsity function about the model, or a model of a function about how small the model is. But then a question that can arise is it really about size and sparsity? And this is something that you can naturally come to think about when you look at something like symbolic models, so this kind of formula. For example, the one on the left is smaller, it has less dimensions than the one on the right. But on the other hand, it has composition of transcendental functions. So if you're not familiar with them, that may be a problem. So a first thing we have to consider now is that given these sorts of features about a model, combining them into some sort of interpretability objective, or equivalently penalty term, is non-trivial. The second point is that how good this objective is going to be really depends at the end on the end user, because interpretability is subjective. And so, for example, a mathematician may prefer this model because he or she has no problem with handling these compositions, and the model is lower dimensional. Another person may really not like those compositions and prefer to analyze the model in parts because there are linear combinations going on here and no transcendental compositions. All right, so we get to a sort of a paradox. We like to think that is the metric to optimize a ML model to be interpretable is itself a black box. We don't know how to create such a objective, such a penalty term to improve interpretability. And this is something we try to deal with in this work. So let me show you how our system works. What we do is we have an interface through which we try to capture which are the features of models that the user finds to be more interpretable. We use this information to train and refine over time an estimator of the user-specific notion of interpretability. These estimations are then used in a bi-objective evolution where we try to maximize at the same time interpretability of the user and accuracy, so that at the end of the evolution, the user obtains a front of models that have trade-offs between the two, and he or she can choose the model that he or she prefers. This estimator is evaluating all these models during the evolution and at the same time keeps track of what are the types of models that make it more uncertain. And to reduce the annotation effort from the user, it is those models that we submit for user evaluation for the user evaluation process. And this way, we learn an estimator that is pretty good on overall in not so many steps. Okay, so the ingredients are as follows. The interface is a web application where all the user needs to do is given two models, click or tap on the one that he or she prefers, and then two new models will be loaded. The estimator we use we call it estimator of PSI, where PSI is the personalized notion of interpretability of the user. Is a neural net that uses dropout at prediction time. So what you do is you give the same data point in input multiple times, and the network makes a prediction, and based on how much variance there is in that prediction, you can get a notion of how uncertain the network is. A nice property of doing this, as opposed to use, for example, a Gaussian process, is that the neural net still resembles and approximates a Gaussian process, but it retains its nice properties of scalability in being trained. The loss function we use, all it does is given two predictions the network makes for the models, the features of the models, and given the label the user gives, the loss function is going to penalize or reward the net based on how far off it is about these predictions. And it's very nice in that the network infers a ranking between models without having any explicit number scalar being needed as a feedback from the user. And that ranking is enough to be used in a bi-objective evolution. What we do is to use a genetic programming, which can evolve this sort of symbolic models in an NSG2 algorithmic setting. NSG2 is an algorithm for multi-objective evolution. We use an implementation from our previous work where we added a simple diversity preservation mechanism to prevent the evolution from stagnating too soon. And then we here as a vertical axis, we also compare two metrics from the literature. One is the simplest possible, which is just the size of the model, the number of components, L. And the other one is a linear model that we machine learned in our previous work from a survey of mathematical formulas that were conducted offline. All right, so the experimental settings are as follows, very briefly. We use a tree-based model representation, which is typical in genetic programming. The features we look at are something like the number of nodes in these trees, the number of nodes that are operations, the number of dimensions, but also what is the maximum length of a chain of consecutive non-arithmetic operations. We have 61 engineering students as participants. An experiment lasts for more or less 10 minutes. And we consider 2 real-world data sets. And here I will just talk about one because of the time. So let me get to the main results. The first thing I want to show you is that MLPy behaves in a reasonable manner. And to do that, let me introduce what this tau is. This tau is a percentile. In particular, when we obtain our front of models at the end of the evolution, we sort them according to growing interpretability, and then tau is the percentile at which we pick those models. So what we see is that for tau, which is the 10th percentile, we have models that are more accurate with respect to the training error, but of course, they can have some overfitting going on, but are less interpretable. And as you'd expect, when tau grows, you find models that are much, much simpler, but so that the train error grows, and so does the test error. All right. Next, what we did is to compare the estimator learned by different students during this MLPy process. So let psi hat I be the estimation of the interpretability of the user for the ith student. What we do is we take a collection of models and we rank them according to these different estimators. And then we measure their disarray, the Spearman-Foot rule, which is 0 when the ranks match perfectly. So what we can find is that on average, the students agree quite a bit because the Spearman-Foot rule is about 0.15, but there is a long tail going on. So there can also be a large disagreement between the users. Another interesting thing comes from comparing these estimators found by different users with the metrics from the literature. And we think it's interesting that phi versus L are on average more afar from each other in the rankings they produce than psi is with phi and psi is with L. So we found something that is somewhat in between these two. Another thing we do is at the end of the experiment, we collect the models found by this evolution by this specific user, and we compare them with models at similar accuracy levels that were found beforehand using phi or L, these metrics from the literature. We put them side by side, and we ask the user, do you prefer this model or this other model? And we don't tell which was found which way. And we do this for different levels of tau, so different percentages of interpretability. So what we see here for tau equals 50, where models are more or less already quite simple, is that it doesn't really matter whether you use psi, phi, or L. However, when the model starts to be more complex, we do see that the majority of the users start to prefer psi over phi, and even more so, psi over L. This brings me to the conclusions. It is, in this paper, we present MLPy and we show that it behaves in a reasonable manner. There are further results in the paper. We find that the estimation can be very different across users. We think this is a really cool result. And that there is a moderate preference for the models found with MLPy. We believe that even though the results are not like staggering, it's still interesting that this moderate preference is found because recall that we involved students with two data sets where they're not necessarily domain expert about, and also the features are quite generic. We believe that if we go domain specific with experts of the problem, we will find even a bigger of a gap when comparing psi with metrics that are not personalized. In future work, we want to show that MLPy can be extended as a general recipe. You don't necessarily need to use symbolic models. You could use other sorts of models, such as decision trees. You could even mix the types of models that you show to the user. You don't necessarily need to use a bi-objective evolution. You could use a single objective reinforcement learning system, and also the estimator can be changed. So this concludes my presentation. I thank you for your attention. And you can find our preprint here and our GP code at this other link. Thanks for listening.